Well, today we're going to roll back the curtain a little bit on something that maybe has been bothering you for a while, and that is, I don't know if you stay up late at night wondering about this. I bet, yeah. So maybe you'll sleep just a little bit better tonight. In 351, you learned that alkenes react with electrophiles, including an acid, and that the HOMO of the alkene, the pi electrons, attack the acidic proton, making a new sigma bond, breaking the pi bond, and making a new sigma bond with the less substituted carbon so that the more substituted carbon can have the positive charge. And then in a second step, you learned that Br will attack that carbocation to generate this addition product in which you've lost a carbon-carbon pi bond and a hydrogen-bromine sigma bond, but you made a new carbon-hydrogen sigma bond and a carbon-bromine sigma bond. This was an addition reaction. That's chapter 10 of 351. But one of the things that maybe troubled you then, and you maybe even had to encounter an example like this, was you probably saw the pi bonds in benzene and you wondered, why don't those react? In fact, you may have done a question with a molecule that had a benzene ring in it and another pi bond, and you reacted with the pi bond that was somewhere else in the molecule, but not with the ones in benzene. And you maybe wondered why. And in fact, you can do this. You can take benzene and HBr and basically nothing happens. And so today we want to explore why. And that's going to lead us to the conclusion that the pi bonds in benzene are more stable than the pi bonds in an isolated alkene. In other words, the alkene is more reactive than benzene. And the question is why? And so one of the first things that emerges if you just look at the benzene structure, and this is something that has been known for a long time about benzene, is resonance stabilization. So if you look at benzene structure, and if we were to number the atoms 1, 2, 3, 4, 5, and 6, we can draw a structure of benzene in which the pi bonds are between atoms 1 and 2, 3 and 4, 5 and 6, or we can draw a structure in which the pi bonds are between 2 and 3, 4 and 5, and 6 and 1. And this gives us a chance to review exactly what resonance means. Some of you still may be holding on to the idea that resonance is just when electrons are hopping back and forth. And that's understandable, but also very wrong. So we need to talk about what it means in a little bit more detail. Let's just imagine what it would mean if you really did think the molecule was alternating between these two states. You may have learned in general chemistry, maybe in 351, double bonds are actually shorter than single bonds because you have more pairs of electrons holding the two atoms together. So if you believed that these two structures were hopping back and forth, in a way, what you would be saying is in this moment over on the left, the bonds between 1 and 2, 3 and 4, and 5 and 6 are short, whereas the other bonds are long. And then we switch to this one, and then now 2 and 3, 4 and 5, 1 and 6 are short, and the others are long. But that's not actually the way it works in benzene. In fact, we know from a lot of data that all of the bonds, all of the carbon-carbon bonds in benzene are equivalent. All of the carbon-hydrogen bonds are equivalent. And in fact, if you look in the NMR spectrum of benzene, there is only one kind of carbon and only one kind of hydrogen. And indeed, the real structure of benzene is intermediate between the bond lengths for the carbon-carbon bonds are intermediate between double bond and single bond length. Some people try to illustrate this by drawing the structure of benzene with this dotted line. Some will draw a benzene hexagon with a circle in the middle. I don't like that because you lose track of how many electrons are there, and that's actually really important for understanding benzene stability. So, is there any questions about what resonance means? Yeah, go ahead.
Well, okay, my question is, with that being said, does that mean all the bonds are shorter in the benzene ring than in a six-membered ring without the double bonds?
Yes, the bonds in benzene are shorter than in carbon-carbon sigma bonds in cyclohexane. Yep. So, another hand? No? Yeah? Question? Okay. Say that again? Yes, we're in chapter 19. And I did press record, so we're good. Forgot that at 9 a.m. last week. Oh well. Okay, so it turns out, go ahead.
Sorry. Could they still be, like, are these still quantified as pi bonds? Because it seems like they're a weird hybrid between sigma and pi.
Are they still quantified as pi bonds? It seems like they're a weird hybrid between sigma and pi. The bond length is intermediate between sigma and pi. The stability of the electrons we will see is actually lower in energy than you would expect for pi. So in that way, stability is sort of intermediate. Sigma bonds are more stable than pi bonds. And so yeah, in that way, the bonds in benzene are more stable than you would expect for pi bonds. Yeah. What else? Okay, it turns out resonance is not the whole picture. It's part of the picture, but it's not the whole picture. And the reason for that is I can draw a 6-carbon resonance stabilized molecule that is not, it does not experience the special stability of benzene. So here is 1,3,5 hexatriene. Which is resonance stabilized, but still not as stable as benzene. And so this is an interesting question that we want to answer. And in order to really understand the answer, you got to know some things about molecular orbital theory, which I know is a source of concern and consternation to many of you. We'll try to go through it, and I'll try to make it really clear what I want you to know versus what you don't need to worry about. All right. Before we dive into that, let's just review what we mean when we talk about a pi bond in an organic molecule. Where does that pi bond come from? Go ahead.
It comes from an alone pair on the carbons. Other carbons?
Comes from 2 carbons side by side overlapping with each other, and I heard p orbital, right? You get the pi bond by the pi molecular orbital comes from addition of the 2 p orbitals together side by side with the same wave function sign. And if we were to draw that on this picture of the molecule, that's above the plane of the sigma bonds and below the plane of the sigma bonds. So that's a pi bonding orbital. Of course, the math of MO theory requires us to mix them together in all possible combinations. So you also have to do the out of, or the opposite wave function sign combination, the minus combination. And when wave function sign switches between 2 atoms, or when wave function sign switches, we call that a node. And we've said before that this pi orbital is a bonding orbital and the pi star is an anti-bonding orbital. Okay. So if we apply that to 1,3,5 hexatriene, we could say, okay, and I'm just going to use a circle to represent the top lobe of the p orbital that we're looking at for this molecule. you would say there's a p orbital on atom 1, another on 2, another on 3, another on 4, another on 5, and another on 6. And you might say the pi bond between 1 and 2 comes from side-by-side overlap of p orbitals on 1 and 2. You could say the same for 3 and 4, and the same for 5 and 6. Here's the jump. 2 and 3 are also adjacent to each other. And 4 and 5 are also adjacent to each other. When you have a string of p orbitals all on adjacent atoms, and they all line up with themselves parallel, line up with each other in parallel, that's called conjugation. And you learned about that in 351. When conjugation happens, the math of MO theory allows us to take the 6 p orbitals that are lined up together and mix them together using maths to get 6 new pi-type molecular orbitals out. And we need to talk briefly about what these look like. It's going to be, we'll spend a little bit of time, but the payoff, it's like the setup to a long joke that isn't that funny. It's going to be kind of painful, but the payoff is going to be good because you're going to understand exactly where the extra stability of benzene comes from. Okay, so when I mix 6 p orbitals together, I'm going to get 6 pi orbitals out. So we could number those from the lowest energy one, pi 1, up to the highest energy one, pi 6. And we're not going to draw all of these unless you make me, but we'll draw enough of them to get an idea of what's going on. The lowest energy orbital is always easy to draw. This is the one where the p orbitals on atoms 1, 2, 3, 4, 5, and 6 all have the same wave function sign. So they add together to make a single orbital that is continuous across the whole molecule without changing wave function sign in between atoms. So above the plane of the page, I have this continuous lobe of electron density. In the plane of the page, there is a place where wave function sign goes to 0 in the plane of the sigma bonds. That's true for all pi-type orbitals. And then below the plane of the page, you have this other continuous lobe. So what we mean by this pi 1 orbital, notice that it has 0 nodes, meaning there are 0 nodes in between atoms. I'm not counting the node that is in the plane of the sigma bonds. Electrons in this orbital, and there are only 2 electrons per orbital, are simultaneously across all of the atoms. So in the MO picture of conjugation, we step away from the idea that 2 electrons are in a bond between 2 atoms. Instead, we allow 2 electrons to delocalize across the whole molecule. And what we mean by these 2 electrons is they're simultaneously above and below the plane of the page all at once. That's their wave-like property. Okay, any questions about where that one came from? Yeah?
This is the pi 1?
This is the pi 1 orbital, yep. Now, it turns out we can draw the highest energy one is pretty easy to draw as well. This is the one you draw when you have a change in wave function sign between each and every atom. So there will be a node in between 1 and 2, there will be a node in between 2 and 3, and so on. That is, the wave function sign changes in between all of the atoms. And this is kind of like our pi star. In the pi star for a single pi bond, the wave function sign changed once in between the 2 atoms. In this pi 6 orbital, there are 5 nodes. And it's pretty easy to recognize this as an antibonding orbital. In the same way that it's pretty easy to recognize the pi 1 orbital as a bonding orbital. And we can continue on. If I were to draw the pi 2 orbital, that would look like it should have just one node if we're following a pattern. And it turns out these orbitals have to follow the symmetry of the molecule. That's required by the math. So if you look at 1,3 hexatriene, carbons 1 and 6 are identical, carbons 2 and 4 are identical to each other, carbons 2 and 5, and then carbons 3 and 4 are identical to each other. So any orbital that we make has to agree with that symmetry. So you have to put the nodes in symmetrical places. The place you can put one node that would be symmetrical is right here between atoms 3 and 4. And so the pi 2 orbital looks like this, with a continuous lobe of electron density on the first 3 atoms, then a switch in wave function sign in between atoms 3 and 4, and then another continuous lobe on the other side. Here, remember, the color simply tells you the sign of the wave function. Every time the color changes, that's you're going through a node. So that's the pi 2 orbital. There is one node, and there are electrons in that pi 2 orbital as well. I'll tell you how you can tell that in just a little bit. Now, I would never expect you to draw these from memory or to come up with them on your own. But what I would expect you to do is, given a drawing of a pi-type orbital, be able to follow the color changes enough to know how many nodes the orbital has, and then based on those number of nodes to rank the orbitals in energy, and then to make some decisions based on that. So for example, you would know that the pi 2 orbital is higher in energy than the pi 1 orbital. Why? Because it's got one more node. Okay. Similarly, and maybe I'll just do pi 3 and then we'll stop there. The pi 3 orbital needs to have 2 nodes. The symmetrical place to put those 2 nodes is actually right here in between atoms 2 and 3, and then between atoms 4 and 5. And so this electrons in this orbital have 3 different sections separated by nodes. And you can tell that there are nodes because you have a switch in wave function sign. Now, counting nodes is a perfectly sensible way to deal with ranking orbitals in energy. But there's one more piece of the picture that we need to deal with to really understand how the orbitals for 1,3,5 hexatriene differ from the orbitals for benzene. And to do that, I'm going to introduce some new terminology. We're going to talk about an individual orbital as having what I'm going to call bonding interactions versus anti-bonding interactions. These are going to be properties of these orbitals. We'll look at an orbital and say, oh, this has this many bonding interactions versus this many anti-bonding interactions. I am defining a bonding interaction that I'll abbreviate as just BI as the number of times when adjacent atoms in an orbital have the same wave function sign. In other words, if you look at an orbital and you look at adjacent atoms and they have the same color, then that is a one bonding interaction. In contrast, an anti-bonding interaction is going to be the number of times when adjacent atoms in an orbital have opposite wave function sign. So if you look at 2 adjacent atoms in an orbital and the color is changed, that is an anti-bonding interaction, which I'll abbreviate as ABI. So, one of the ways we've talked about orbitals is writing the number of nodes that they have. We're going to do the same with the number of bonding interactions and anti-bonding interactions. So in this pi1 orbital, how many bonding interactions would you say that there are? I count 1 between 1 and 2, 2 between 2 and 3, 3 between 3 and 4, 4, and then 5. 5 times when adjacent atoms have the same wave function sign, and 0 times when they have opposite wave function sign. And it turns out we can subtract the anti-bonding interactions from the bonding interactions to get an overall sense for whether this is a bonding orbital or an anti-bonding orbital. Of course, it's obvious here. This is, there are 5 net bonding interactions here. Therefore, we would conclude that pi1 is indeed a bonding orbital. You could say up for pi6 that there are 5 anti-bonding interactions and 0 bonding interactions. So you would conclude that pi6 is an anti-bonding orbital. Similarly, we can do the analysis for pi2. How many bonding interactions do you see there? 1, 2, 3, 4. Do you see where I'm counting them? 1 here, 1 here, 1 here, and 1 there. Number of times adjacent atoms have same wave function sign. How about anti-bonding interactions? Just 1, right? So I'm going to subtract the 1 anti-bonding interaction from the bonding interaction. I will conclude that there are still 3 net bonding interactions. So this is still a bonding orbital, but it's not as low in energy as the one that's below it, right? That has more bonding interactions. In a way, we're just counting nodes, but we're doing it in a slightly different way. Finally, the pi3 orbital, we would say, has 3 bonding interactions, but 2 anti-bonding interactions, so net just 1 bonding interaction. And you can use this to rank orbitals in energy, even across molecules. For example, if I zoom out and go back up to a pi bond, I would say that a pi bond has 1 bonding interaction, a pi star has 1 anti-bonding interaction. So I could conclude from that this pi3 orbital with 1 net bonding interaction is about the same in energy as a pair of electrons in an isolated pi bond, whereas these 2 are more stable than expected for an isolated pi bond, and these 2 are even more stable than that. This gives you a sense for why resonance is so stabilizing. It allows electrons to experience more nuclei and to delocalize over more space. Okay, questions about that? Yes?
So for pi6, why would you not consider any of the p orbitals part of the quads?
In pi6, the wave function sign changes between each atom. And so that's 5 anti-bonding interactions. There's no places in pi6 where the wave function sign stays the same between the 2 atoms. And remember, these are not, when you look at pi6, you need to see 1 orbital that looks like that, not 6 different p orbitals. Yeah?
So just making sure I understand here, like where the nodes are, even though pi6 is drawn on a continuous system, there aren't going to be any
Right.
bonds there, right?
Even though pi6 is drawn on this molecule where I've got the pi bonds there, electrons in that orbital would be really high in energy and not contribute to bonding. Yeah. Okay. So pi3 is going to be the molecule's HOMO, our highest occupied molecular orbital. Pi2 is going to be the LUMO. Now, we're going to discuss what happens when we take this same way of making orbitals, but for benzene, remember with benzene, we've still got an alphabet of 6 p orbitals, and they're still going to make 6 pi molecular orbitals but the geometry is different. Benzene is cyclic, so instead of having 6 p orbitals in a line, for benzene, we're going to have 6 p orbitals in a circle. Now, as with 135 hexatriene, our lowest energy pi1 orbital we're going to get from the all plus combination of the 6 p orbitals. That is, we're going to draw pi1 for benzene. Oops. And we're going to draw what we would get if you allowed atoms 1, 2, 3, 4, 5, and 6 to have the same wave function sign all the way around. In other words, what we're going to get for benzene is an orbital that kind of looks like this. Here is the lobe above the plane of the page. Here is the lobe below the plane of the page. And it looks essentially like a hamburger bun where the orange part is over the plane of the page. The sigma bonds of the benzene ring are in the plane of the page. And then you've got the pink lobe below the plane of the page. Now, that orbital, like the pi1 of 135 hexatriene, has 0 nodes. Let's count the number of times adjacent atoms have the same wave function sign. 1 there, 2, 3, 4, 5, 6. Gasp, that's the payoff there. Thank you. That was gratifying that you gasped out there. That made me feel like I'd done something good today. So 6 bonding interactions. The fact that benzene is cyclic allows us to pick up 1 extra bonding interaction. Exclamation point. 1 more than the linear counterpart. 135 hexatriene. So that's some of the special stability that comes with benzene. Our lowest energy orbital is more stabilizing because there's 1 more bonding interaction. Now we'll draw a couple of the other orbitals for benzene. If we wanted to draw where this one was, I would actually put the energy of the pi1 orbital for benzene lower than the energy of the pi1 orbital for 135 hexatriene. Let's now look at how to draw an orbital for benzene with 1 node. It will turn out that for the linear 135 hexatriene, there was just 1 way to draw an orbital with 1 node and still obey the symmetry rules of the molecule. Because benzene's structure is different, there are actually 2 different ways to draw an orbital with 1 node. You can draw it like this, where the node goes through atoms 1 and 4, or you could draw it like this, where the node goes through the space between atoms 1 and 2 and between atoms 4 and 5. Those are 2 equivalent and valid ways, while keeping the symmetry of the molecule, to draw orbitals with 1 node. Let me show you what the one on the left would look like. That would have a lobe of electron density here above the plane of the page and below the plane of the page, and then another one here. There would be a change in wave function sign as you go from above to below, and then again as you go from left to right. This orbital would hold a single pair of electrons, and they would simultaneously occupy this space here and this space here, but they would have 0 magnitude along the blue line. That's 1 node. On the other hand, the orbital that looks like this with the node that bisects the space between the 2 atoms sort of has this kidney-shaped structure where there is a switch in wave function sign between the 2 atoms, across where the node is, And we'll draw it like this. Now, you already probably believe that these two orbitals are equal in energy because they each have one node, but we can prove it by summarizing the bonding versus anti-bonding interactions. The orbital on the left, which we're going to call pi 2, has two bonding interactions, one here and one here. It has 0 anti-bonding interactions. Some of you are going to see this node and say that's one anti-bonding interactions, but remember that to count as a bonding or an anti-bonding interaction, adjacent atoms have to have opposite wave function sign. 5 and 6 do not have opposite sign. 5 is positive or whatever, and 6 is 0. So that counts as neither bonding nor anti-bonding. We simply don't count it. That's true whenever a node intersects with an atom. In contrast, we would say that pi 3, the one on the right, has 1, 2, 3, 4 bonding interactions, and then 2, one here and one here, anti-bonding interactions, because the wave function sign switches between these two adjacent atoms and again between these two adjacent atoms. So we would call that 2 anti-bonding interactions for 2 net bonding interactions overall. So we would conclude that pi 2 and pi 3 are equal in energy. They have the same wave function sign. And then compared to the pi 2 and pi 3 from 135 hexatriene, they're somewhere in the middle. Pi 2 for 1,3 hexatriene had 3 bonding interactions. Pi 3 for 135 hexatriene had just 1. So we're going to put the energy levels for pi 2 and pi 3 somewhere in the middle. Okay. Then if we look at the number of electrons that benzene has that are involved in resonance, it's 2, 4, and 6. So we fill up pi 1 and pi 2 and pi 3. And then it turns out there are 3 other antibonding orbitals for benzene. We'll call them pi 4, pi 5, and then pi 6. I won't draw them. They're in your text. Pi 6 is easy. You could draw it. It would have 1, 2, 3, 4 nodes. And it would be what you would get if you had every p orbital out of wave function sign. Opposite wave function sign is the one next to it. There would be 6 antibonding interactions in the pi 6 orbital. So notice what being cyclic does to 135. If you imagine transitioning in your brain from 135 hexatriene, making the connection, adding that extra connection lowers the energy of pi 1 by 1 bonding interaction. For pi 2 and pi 3, it sort of takes him to an intermediate average level. Pi 2 used to have 3 bonding interactions, now it only has 2. Pi 3 used to have 1 bonding interaction, now it has 2. Yeah?
How many nodes does 4 and 5 have?
4 and 5 should each have 3 nodes. Oh, you know what? Thank you for asking that because I got that exactly wrong. 1 node, 2 nodes, see I can't count, and 3 nodes. I told you you would be fine in this class if you could count, and that is right, but sometimes I cannot. The other thing I always get wrong first time is I get my left and my right mixed up. I have no idea why. It's genetic though. My grandma used to tell a story. I mean, there's all kinds of stories, but she used to say that in order to get my grandpa to recognize his right hand, she'd have to say, "Throw a rock, Dale, throw a rock." He's, okay, I throw a rock with this. Okay, that's my right hand. Really smart guy, actually, really great guy, but left and right was not his strong suit, so neither is it mine. Okay, so now you know where the extra stability of benzene comes from. And now you know something about the structure of molecules like benzene in their molecular orbitals. This is really important. Notice that the orbitals come one that's really low in energy, and then pairs of equal in energy orbitals. There's a mathematical term for that we use. That's called, the term is degenerate. That doesn't mean of dubious moral quality, it just means equal in energy. You will see that even if the structure of the molecule changes, if it's like benzene, it's going to have this same pattern of pi molecular orbitals. That is, one that is low in energy and then higher in energy degenerate pairs of orbitals. And that's going to be the origin of a rule we're going to have for counting the number of electrons and determining whether a molecule is like benzene or not. The special stability of benzene is a term that we're going to call aromaticity. This is the special stability we get from benzene that other molecules can have too, when they are resonance stabilized and cyclic and have the right number of electrons. So here are going to be our criteria for aromaticity. The molecule has to be cyclic. We already said that. If benzene weren't cyclic, we couldn't pick up that extra bonding interaction. The second is they need to be fully conjugated. What do we mean by that? We mean each atom has a p orbital that is parallel to or can line up with all the other p orbitals. If you know a little bit about hybridization and molecular geometry, a prerequisite or even a consequence of that is that the molecule is planar. Benzene is planar. Each of the atoms in benzene is sp2 hybridized trigonal planar. The p orbitals all have to be parallel with each other. The only way to do that is for all the atoms to be in the same plane in benzene. Okay? Okay, cyclic, fully conjugated, planar. And then a third requirement, we need to have the right number of electrons. And there is a rule that defines what the right number of electrons is. And that rule is called the Huckel rule, with the umlaut. And that rule is that if you have 2, 6, 10, 14, 18, etc., you could be aromatic. If you like mathematical series and patterns, the pattern is 4n plus 2, where n is an integer starting with 0. Okay? Sometimes people get confused about what n means. Is n the number of atoms? No, it just defines the possible number of electrons that can be that a molecule can have and be aromatic. And by number of electrons, I mean number of pi electrons. That is, number of electrons involved in resonance. So the number 6 jumps out at us. That's true for benzene. Let's look at what having 6 electrons does for benzene. 6 allows benzene to fill the lowest energy orbital. That's the 2 in the 4n plus 2 rule. And then it allows us to fill this degenerate pair of orbitals, each of which can take 2 electrons, but overall they can take 4, right? That's the 4n. If you follow the pattern of 4n plus 2, you will always fill the lowest energy orbital, and you will always fill completely the remaining degenerate pairs of bonding orbitals. That's what makes a molecule aromatic. Imagine if benzene had 2 fewer electrons. So let's just draw sort of the first 3 orbitals of benzene, pi 1, pi 2, and pi 3. Imagine we only had 4. We'd fill the lowest energy one. Then what do we do with the remaining 2? 1 each with parallel spins. That's Hund's rule. And that molecule we just made is a diradical. It's got 2 unpaired electrons, and it's especially unstable. So Huckel also has a rule for recognizing what are called anti-aromatic compounds. These are compounds that are less stable than you would predict for a conjugated cyclic molecule, And the way you recognize them is they have 4n electrons, where n is again an integer starting with 0 and going up. In other words, 4, 8, 12, etc. Molecules that are cyclic, planar, fully conjugated, but have the wrong number of electrons are anti-aromatic, and they are especially unstable. I'll give you some examples of that. All right, so for example, let me show you an anti-aromatic molecule. This is cyclobutadiene, C4H4. And it turns out that the pi orbitals for cyclobutadiene look exactly like we would predict from our analysis above. That is, you have one orbital that's lower in energy, a pair of degenerate orbitals here, and then a higher energy orbital here. You fill up the orbitals with the available electrons, and you have 2 in this lower energy orbital, and then you have only 2 in the degenerate pair, and they are not paired with each other, they're separate. So cyclobutadiene reacts like a diradical. Unpaired electrons are unstable. We would say that it is anti-aromatic. It's even worse than that, for reasons that we'll maybe talk about in a little bit more detail next time. You look at cyclobutadiene and you're like, that has 2 pi bonds in it, but it actually only has 1. These 2 are at about the energy level for a non-bonding orbital. And so cyclobutadiene is especially unstable. We'll have more to say about that later. For right now, we need to practice recognizing aromatic versus anti-aromatic molecules. So let's do that. Here is a stop sign molecule, cyclooctatetraene. So, cyclic, yes. Fully conjugated, yes. How many pi electrons? 8. So that's from the 4n rule, that's anti-aromatic. If we were to draw the orbitals, and I'll show you how to do this, there's a mnemonic device that we'll learn next time, but the pi molecular orbitals for cyclooctatetraene look like this. We would fill these two, and then the higher energy ones would be like this. Basically, again, like a diradical. I want you to put an asterisk in your mind by anti-aromatic. There's more to the story there that we're not saying yet. Right now, it's enough to determine, is it cyclic, is it planar, is it cyclic, is it fully conjugated, and then does it have the correct number of electrons. If it's 4n plus 2, it's aromatic. If it's 4n, it's anti-aromatic. There's some nuance in there, and there's going to be some confusing answers you're going to get from your textbook. I'll try to address that next time, but it's better if you've struggled with it for a little bit so that the answer can make sense. Okay, it gets more complicated when we start incorporating atoms that are not carbon or hydrogen. So, behold, the molecule pyridine. Aromatic or anti-aromatic? Yeah, I don't know. You're not sure what to do with that lone pair on the nitrogen, are you? Does it count or does it not count? Now remember, in order to count, the electrons have to be part of the pi system. That means they either have to be in a p orbital or in a pi bond, but part of the conjugated pi system. So let's look at that nitrogen. Nitrogen is what hybridized? sp2. You can tell that because it's surrounded by 3 things, 2 carbons and a lone pair. This sigma bond comes from one of those sp2 orbitals. This sigma bond comes from the other. Where does the pi bond come from? P orbital, right? So we check off the p orbital. Therefore, the only place that lone pair can be in is what? The lone pair is in an sp2 orbital. Now, what does that mean? Is the lone pair part of the pi system or not? Not part of the pi system. The reason it is not part of the pi system is that the sp2 orbital is perpendicular I can't spell that, perpendicular to the p orbitals. It can't be part of the pi system, therefore it doesn't count. You're going to have to do that analysis with each lone pair on a nitrogen or oxygen to determine, does that lone pair count or not? Is it in the pi system or is it not? For pyridine, the molecule we've just drawn, 2, 4, 6, we don't count the lone pair. We've got 6 pi electrons, so yes, indeed, this is aromatic. A slightly more complicated one. Lots of nitrogens, lots of lone pairs. Here's a hint. One of them counts and one of them doesn't. Which one? Which one? Think about it. Yeah. Okay, here's a hint. What do you do with lone pairs that are adjacent to pi bonds? Some of you are looking at this one and saying, I think that lone pair is in an sp3 orbital because that's what I've learned for nitrogens that are surrounded by 4 things. 2 carbons, a hydrogen, and a lone pair. That's usually true unless the lone pair is adjacent to a pi bond. If the lone pair is adjacent to a pi bond, it will be in a p orbital so that it can participate in resonance, because remember, resonance is stabilizing. So yeah, you expect that lone pair to be in a p orbital. You expect the nitrogen to be sp2 hybridized. What about this one? That's the same situation we saw over here in pyridine. You got a nitrogen that's sp2 hybridized, the pi bond, the p orbital's already taken up with this pi bond. The conclusion is that that lone pair is in an sp2 orbital. Therefore, 2, 4, 6, this molecule is aromatic because it's got 6 pi electrons. It is cyclic, fully conjugated, and has the right number of electrons. Some of you, unfortunately, I'm thinking probably didn't quite get that, so let's say it again, because I've asked questions about it on a test, and people come to me after the fact, and they're like, oh, you did say that, didn't you? So let me warn you now. Nitrogens that aren't involved in pi bonds but have lone pairs on them, if those lone pairs are adjacent to pi bonds, the lone pair is going to be in a p orbital so that it can participate in resonance. Look for that. Okay. Other questions? Okay, well, story time. I'm not sure whether or not to do this. I didn't do it at 9 a.m., but here we are. Got a couple extra minutes. So some of you know professors submit applications for grants so that we can do our research. We need external money from the federal government to do our research. I've got a deadline that was today, and as of last week, I was like, I'm not sure this is going to get done. And I felt like the Lord was telling me, I don't care, do it anyway. So I said, all right, Lord, if we're going to do that, I'm going to need your help. I'm going to need some miracle days of writing. I mean, the miracle is right here. This is a 12-page document, single-spaced, 11-point font, and it's done, and I should not have been able to get it done. This isn't because of me, but it's because of the Lord. If you trust... Now, I could submit this to the government, and they could send it back and say, this sucks, we're not going to fund it. That may still happen, but I feel like it's a miracle, and I've even gotten to that point. You'll feel that way, too, as you're preparing for my exam. Just trust in the Lord, and things are going to be okay. All right, see you next time.